welcome to Ladyada.
Hey everybody, and welcome to my desk. It's me, Lady Ada, with me, Mr. Lady Ada on camera control. I got some hardware I've been working on. I wanted to show off. But Mr. Lady Ada, did you want to do a little intro first, or do you want
Well,
that later?
later on when Lady showed the um, Circuit Pirate, this was the photo we posted up, so I thought it was a glimpse into what's going on here.
This is
Lady
my life.
is designing electronics, taking care of Kiddo, doing all the things. Eagle Cat is charging her 2 seats, thinks that's unfair, but that's okay. And we also posted up about this really cool project, and we'll talk about the logo more.
Yeah,
But without further ado,
yeah.
what's new
So,
with you?
okay, so we stock we used to stock the Bus Pirate in the Adafruit Shuffle. You don't have to go to the computer because you can see it. This is the Bus Pirate, which is a really cool like hacking toolkit that uses USB serial commands. You can actually see the FTDI chip here.
Public domain too.
And it was, yeah, no, well, we'll get to that. Designed by Ian Lesnar. This is version 3.6 and design. You can see, well, when we go to the computer, we'll see it's designed April 2012. So this is like 10 years old. But what's really cool is that like there were a lot of people who wrote scripts, and while I think a lot of the functionality of like having a USB to bus device has been replicated by like the Binio, which we stock, U2IF, the FT232H. There are a couple of things that the Bus Pirate was really good for. Like it had a lot of protocols built in, which I thought was kind of neat. So like you could have like it could act like a mini device or a keyboard, and it kind of knew everything. You didn't have to like bit bang all of it. It also had a couple neat things like the chip used, the PIC12F, is 5-volt input compliant. So it was a 3-volt chip, but you could use the 5-volt signals, and so that was kind of nice because you could use it with uh, devices that like LCDs or maybe EEPROMs that were 5-volt logic. But unfortunately, it was discontinued. We've been stocking it for a very long time, and we went to do a reorder with Seed, and they were like, "Oh, because of the chip shortage or something, or maybe there's currently a delay. We don't know when we're going to get more." A little bit of a bummer. And so for now, it's discontinued. Sometimes things get discontinued in the Adafruit shop, but I don't want to promise something unless we have some good sense that we'll get it again. And I don't know when that's going to be. There's also the Bus Pirate 4, but I guess that's also not available. And right now, so let's go to the computer because I'm going to do a bunch of computer stuff. Um, so right now, we still have the page up, but we recommend people check out the Good Fet by Travis Goodspeed. Also out of stock, but probably we will be able to get again. Very similar device, USB serial converter to like a toggler. One thing that was really nice was that this could do JTAG. So it does like it was I2C one wire SPI. Like one wire, for example, is a very rare thing for USB to like bus devices to do because it's a freaky thing. MIDI, PC keyboard, LCDs, pulse width modulator, frequency generator, it just like bus traffic sniffers. A lot of cool stuff. Oh, could act as an AVR programmer. It just had a lot of like nifty things built into it, a lot of support. So we really like this. We couldn't get it anymore. And instead of just running the board on my own and trying to like get the chips, which I could probably do, I could probably refabricate it based on the files, which are all public domain and under Creative Commons 0, which is actually really neat. It's pretty rare to see devices that are CC0. That means like completely free for all. You can use it for any purpose whatsoever. But public domain, and just very cool that Ian Lesnett released it that way. But I was thinking, instead of just remaking this because there's this Bus Pirate 4 and then like maybe there's better chips anyways, I thought let's maybe remake the design because um, actually a few years ago, um, so unfortunately the files got rewritten because they were um, I worked on the files in 2017 and then I updated the EagleCAD files, and so that's why it says 2023. But originally they were in 2017. I had this idea when we first did the RP20, sorry, the Circuit Python for the SAMD21, I had this idea of like, oh, well, maybe we could like kind of like make a version, like something that was like a tool, like a hacking tool thing, but it would be running Circuit Python. And I didn't think it would mimic the Bus Pirate. I just thought it would be like the same shape, and maybe you'd be able to like run commands, but the commands would be in a Python script rather than USB serial converted. And I worked on this for a bit, and let's just do, you can kind of see, hold on, let me turn on the, whenever I video, I like to turn off the TDocu layer because I feel like it shows the components best. So we had a, actually, hold on. Very good, that's much clearer. Okay, so you had a micro USB, a NeoPixel. This is some SPI flash that connected to the SAMD21, the same chip used in like the Metro M0 and the Cutie Pie. Reset button, 3-volt internal, 3-volt external, 5-volt external power supply. These are switchable, which I think there's like a couple little details about the Bus Pirate really neat, like the 3-volt power supply, the 5-volt power supply to your device. You could switch on and off by enabling, disabling the regulators, which is really handy. Sometimes you have chips that are like get into a freaky state and you're just like, okay, gonna just power cycle you, and they're like back to normal. Crystal analog switch, and then that 2x5 header, and resistors, and there's not actually a lot on the Bus Pirate. A lot of it is firmware. It actually got a little of that code written that would have it do like some of the basic I2C and SPI and bit banging, toggling functionality, but the SAMD21 was really minimal, and I didn't want to write the code in Arduino. I was like, oh, let's see if I can write it all in CircuitPython so I could actually get it done with less than a year. And I ran out of memory of SRAM. And then I was like, well, like there is a Bus Pirate, and like, what was the point of doing this anyways? And so I kind of shelved it because it didn't, there wasn't much purpose when you could still get the Bus Pirate. But then, now that you can't get it, I thought, like last week, I was chatting with Tan Newt Scott, the lead CircuitPython developer, and he kind of wanted he wanted something to distract him. He was like, oh, do you have any projects that you can distract me with? Because I don't want to work on this IMX stuff for a week or two. And I said, well, there was this Circuit Pirate thing, the Bus Pirate port to CircuitPython. Do you want to try revisiting again? And he was like, oh, yeah, that sounds like a great project to just like totally lose 2-3 weeks in. Let's do it. So he would work on the firmware, and I said I'd finish the hardware. So I decided to re-spin it. So the one thing is that, and there's trade-offs. I wanted to keep the price low because, that's one of the things that people liked about the original Bus Pirate. It was cheap. So I was like, can I make it basically $20? But I didn't want to make it about the same size. And I wanted to have basically the same functionality as much as possible. So this is what I came up with so far. And this is, I think I'm going to revise it a couple times, but I wanted to get some, proto PCBs on order. So the original had a mini USB. Hold on, I can pop this up. 3.5 is kind of close. 3.6, I think, just has rounded corners. This is designed in 2010. I mean, this is a very old project. So mini USB there, but mini USB is I think out of date now. Wait, let me close this one and close this one. So I went with USB Type C. Boot and reset button, and the boot button can also be a user button, and that's because it's got an RP2040, wide RP2040, cheap and available. I can't get the SAMD51. Again, the SAMD21 is too small. I didn't want to go with another chip that I didn't know I could easily get. And, the whole thing about the Bus Pirate is it's a pin toggly bus thing, and all the protocols that the Bus Pirate supported, like LCDs and PS2 keyboards, one wire, I2C, SPI, bit banging, whatever, one wire. That's all supported in CircuitPython for the RP2040. The only thing that wasn't supported is JTAG, so we'll probably have to write a little helper to do, the JTAG toggling. And I want it to support SWD, actually, because that would be cool if it also could do like a pico probe type behavior. And it has plenty of memory, to be able to handle all of that in Python. There's also an 8 MB flash chip. I still have those regulators, a 3 volt, 3 volt and 5 volt. The 5 volt I actually updated to be, these are all 500 milliamps. The original was like 100 milliamps. I updated these all to be 500 milliamp regulators. LEDs for power, data transmission reception. I think we actually added this into CircuitPython a really, really long time ago, where you could have the UART, the USB data, send RX and TX, a mode LED, because there's a couple different modes, like binary, non-binary, the 5 volt power supply output to 3 volt power supply output, so you know if your power is output. Same pinout as the 2x5 header on the original. And then I added a couple other things. So you got, the NeoPixel, and this is a STEMMA QT port, because Scott was like, I'm going to use this mostly for debugging I2C, and you could like sniff I2C. So this is I2C on a separate I2C bus than the header. So there's like 2 buses. A mode switch, and this is, we need a switch because in CircuitPython, you normally get a UART REPL, and then you can have a second UART for data, right? So we're going to have the commands that you send to the Bus Pyrate clone. It's just going to send the data over the secondary UART. So you have the REPL still for debugging, and if you want to, you can control D and like do stuff. But the main menu command interface is going to be to the second UART, and we want to have a switch to enable or disable the REPL, because we thought it would be confusing if there was 2 COM ports. People would be like, oh, which one am I supposed to use? So when you put it into program mode, the REPL would show up, and then if you do in user mode, it would disappear, because you can do that. You can dynamically change the USB availability. And then the analog switch, and then, there's a lot of components. You need a lot of capacitors to support the RP2040, and there's like a crystal over here, and all the good stuff. And pretty much it's the same size and shape, but USB-C instead of mini, 2 buttons, STEMMA QT, mode switch, same pinout, and a couple extra LEDs. I figured, why not just throw them on there. Couple of things, though, that were a little annoying is, and we'll have to figure out how I'm going to do this. So the original Bus Pyrate, the pinouts that they did, like the marking is only the SPI. So it's like clock, MOSI, MISO, chip select. So microcontroller out, sensor in, microcontroller in, sensor out, chip select, and SPI clock. And then those pins would also be multiplexed with the I2C and UART. The problem is that the PIC 14, it had their own pin mux that was very specific. And so it turned out that the SDA and UART TX and MOSI pin were all on one pin. And the RX and MISO, like they were very like, oh, these are the pins that are available. But that's not what's available on the RP2040. The RP2040 has different pinout capabilities. So this is what the pinouts are. It's TX, MISO, SDA. And so that's like, that doesn't match here, and RX and CS are the same, whereas here it's RX and MISO. So there's like this mismatch of what the multiplexing can do. And so the Bus Pyrate 4, when I looked at the schematic for the Pyrate 4, if you look at their schematic, what they did, I didn't look at the detail, but what looks to me is, because there's this SPI set here, and then if you look, it's duplicated down here. So I think what happened is they actually just connected 2 sets of pins to one IO, and they just manage it so only one is driving, one of those pin sets is driving, depending on whether you want I2C or UART or SPI. I thought about doing that, but there's not actually a ton of, there is plenty of pins and I could do it, but when talking to Scott, because I was like, okay, here's this issue. We were like, well, we can bit bang I2C and UART pretty easily, particularly with PIO. Like UART, you can do quite well. Normally UART's quite hard to do with bit banging, but the PIO makes it very easy. And so we actually made this the hardware SPI port. And I put little jumpers on the bottom, you see. So if I change my mind, I can like cut them in, like maybe like, quickly rewire them as necessary. So, we'll see. This is an experiment, and then the second part is this analog mux, which I won't go into a lot of detail. Maybe next time, because I want to get to the great search. But they use an analog switch to turn on and off the pull-ups from the external voltage, like the output voltage. Sorry, yeah, the external voltage, which comes into the Circuit Pirate board, and then using this, you can enable or disable all 4 pull-ups at once. And you can see these are the pull-up values, and then they connect or disconnect from the external based on this value. And I thought, analog switches are kind of neat. So I thought I would make that the great search. I don't know if if you want to wrap up anything with the Circuit
Yeah,
Pirate. I mean, there'll be more to
you
come.
can check on the socials on our blog. We have the schematic, the rendering that we're starting
It's
on.
still,
We're playing around
yeah.
with a logo, but let's kick it with the great search.
Okay, let's kick it.
Where in the world is that part I need? The great search with Digi-Key.
The Great Search brought to you by Digi-Key and Adafruit. Every single week, Ladyada user powered of engineering help you, yes, you find the things you're looking on for and with Digi-Key.com.
Okay.
What's up?
Okay, so let's go to my computer. So this week I've been working on this design, which is pays homage to, is a derivative of an open source project called the Bus Pyrate. And one thing this project did, which I thought was interesting, was it uses an analog switch to enable and disable pull-up resistors from these 4 GPIO pins to an external voltage, which might vary. And I thought it was interesting because I was like, oh, why didn't they just use like a bunch of transistors? You could do this with a bunch of FETs. And I was like, oh, like it would take a lot more board space up. And it might be more expensive than just plopping down one analog multiplexer slash switch. And then I realized, we've never talked about this kind of part. We often have buffers, or we have maybe op amps. But an analog switch is kind of a cool, weird thing in between. It's made up of MOSFETs, and it's basically, you could think, hey, I can connect and disconnect some things by, connecting up some N channel and P channel MOSFETs, and you basically disconnect and connect a pathway between 2 I/O pins. Particularly for analog voltages is what they're good for. They're called analog switches. Although of course you can do them for digital signals, they're just not going to be as fast as they're best used for analog. You can use them digital, but of course there'll be a limit of how fast the frequency you can push through them is. And of course this is a replacement for mechanical switch, but there are some trade-offs. Just because they're called analog switches doesn't mean they replace a switch. There's a couple things to watch for. So first off, you can go to Digi-Key and search for analog switches as opposed to mechanical switches, right? Which are the clicky things. And there's a couple zones. There's like, a special purpose, but there is, one main section for them. And there's a lot of settings, although not every setting is covered. So the upshot is they're silicon chips, and the most popular ones are the ones that are kind of borrowed from old CMOS logic. So this design used the 4066, which is a 4-channel SPST switch. But there are other ones too, like the 4051, and of course a lot of the CMOS logic, as it became more modernized and more durable. You're going to see it called 74X, 74HC, VHC, VHT, whatever that series. So the 4051 is a multiplexer, demultiplexer. So what's kind of neat here is that you have one, you have one of 8 decoders. So this one is a single pole octal throw, SP8T. So used to connect one input, Z. So Z is the input or output. That's the thing. It's analog. It can go bidirectionally to 8 different outputs. It's basically like an 8-way mechanical switch. And then you use the 3 logical inputs, S0, 1, and 2, to select which of the 8 outputs or connections you'll have Z connect to. You have VCC, VE, power, and ground. You'll notice a lot of these, because they're meant for analog signals, which used to be like positive and negatively referenced, like -12 to +12. It's not that unusual to see these chips have pretty big power supply possibilities. So you can usually, while you could run them 0 to 5, running them like -12 to +12 is there are definitely versions for that. There's enable and then a ground. So a couple things to be aware. First up, there is so this one has, wide input range of -5 to 5, but of course your power supply has to be beyond that, usually maybe plus or minus 1 volt. You can't use like one of these analog switches that's powered off of 3 volts and use that to switch 5 volts. Like your signal input output cannot be above or below the rails, except for like one weird situation where it can. On resistance. So unlike a mechanical switch where you have a resistance of like 0.01 or 0.1 ohms, like it's almost nothing, there is a resistance. So these low-cost 40XX series, you're going to get 10, 50, 100 ohms. So, just be aware that there's some impedance. This is not a power, like, mechanical switch, you can easily get ones that give you amps of current through. This one, you're not going to be able to drive that much current through. And there's another limitation of how much, not only is there resistance, but there's a limit of how much current, usually looks like, 20 milliamps or so between each input and output. So this power supply, for example, you can run it up to plus minus 5 volts or 0 to 10 volts. You can do either as long as the total differential is 10 or less. So that's like one example, but there's others. The 4051, the 4052, which is a 2x4 switch. So this would be good for like a stereo signal. 2 inputs. And then 4 outputs for each, 2 options for each. So here you've got 1Z and then goes to, Y0, 1, 2, 3, and then 2Z, which goes to this set. So it's like 2 to 4, 2 stereo switches and 4 options each. So there's like every which combo you could ever want. There's SPST that, normally open, and then you'd have to do something to connect them, SPST switches. There's ones that are single, just like one little switch, different resistances. Again, like I said, the inexpensive 10, 20, 40 cent chips are going to be a couple ohms, but you can get one that are, very low ohmage, under 1 ohm resistance. You also get ones that are massive, 64 circuits, which is kind of bonkers. I can't even imagine how big this is. Yes, this is like a beast. 44 BGA, but you can get it. All is available. What we want actually, so this is the 4066 series. I just want to, show a couple options in the 4066 family. Let's just look at the active ones for now. And only surface mount, although they are available in through-hole, by the way. I did use them in lab when I was a student. They were very popular. There's a couple standard packages. There's the DVQFN. There is the SOIC. And the TSOP. Now, we're actually going to use the TSOP in our design. And the LVC is a good family to use. It can run from 3 to 5 volts. And I'm trying to remember if this voltage, so I would run it at 5 volts and then, I'd use 3-volt signals to enable it. But then if the external voltage was higher than 3.3, it would be fine for my switch. I wouldn't have to dealing with the above the, it's a little tougher to switch voltages that are above your power supply rail. So I think this is why the original designer decided to go with the 4066. So your enable switch is 3 volts, but the external voltage is 5. You power this from 5 volts, and then now you can turn on and off and connect those pull-up resistors to the through the analog SPST. without having to worry about like, oh, now I need like 2 layers of FETs to make that higher voltage for switching them. So the VHT, so this is probably what I'm going to end up going to the LVC. Sorry, the LVC series is good. Runs from a fine voltage. You know, it can fairly low on resistance, 6 ohms, not going to affect it. Each switch can handle 32 milliamps, plenty. Because again, it's just a pull-up resistor, and it's also fairly inexpensive. So, you know, you're talking about like 40 cents in a reel at a time. So a good price. And so, you know, why not just do this with FETs on your own? You can, but for 40 cents, you just drop it down and you're ready to go. So this is my great search pick of the week.
Where in the world is that part I need? The great search with Digi-Key.
And that's our show for the week. Thank you so much, everybody. We have a full lineup of shows this week. Lots of surprises. We've been posting lots of videos and more every single day. So we will see everybody during the week. Thanks so much for joining us. It's very much appreciated.
Thank you.
Bye, everybody.
Have a great week.